Hello everyone. In the previous part of the lecture, we had recapped the fundamental idea which led to the algorithm of the familiar algorithm of uh, minimizing a function, a simple function. So we want to export that idea, as we had mentioned at the end of that lecture, uh, to the extremization of these kinds of integrations which we were talking about in our first lecture. So we had said that we would be restricting our attention to integrations which would be dependent on x, y, and y dash. It is very much possible to extend our ideas to integrations which are dependent on higher order derivatives, but just to keep the algebra relatively clutter free, we are going to deal with this restrictive thing. Now, please note that here the y itself is a function of x. Okay, so it is as if we are dealing with a function of functions. This integration here, it is dependent on the choice of the function uh, that we are choosing here. Okay, so it is as if this integration is a function of a function. So that kind of an entity is what is referred to as a functional. Okay, so this is a function of functions. So what we say is that we are now interested in developing the method for extremization of functionals. So how do we go about doing it? As we mentioned earlier, we are going to export the same idea that we had done for the extremization of functions. So there we had explored the neighborhood of the point x equal to a for the minimization. In a similar fashion, here we are going to explore the neighborhood, so to speak, of this function y. Okay, so let's say that it is at y that we obtain the actual minimum, but you don't know what y is. Of course, it is a generic y. So we want to explore the neighborhood of y. So what we basically mean by the neighborhood of y is that y will have certain characteristics. Given a certain problem, it will have a certain nature. And as we mentioned in the first lecture, if we were to speak very mathematically in a mathematically formal way, we would say that there would be a certain set of criteria which would let us define a set of admissible curves y, and we would make our choice from that set of admissible curves. So it is in that sense that we are talking about the neighborhood of y. So we take a function which is not exactly y, but almost like y with a little bit of variation here and there. Okay, so the function that we choose will be like this. So the neighborhood of this thing, that will denote by y plus epsilon eta. Okay, now why this strange way of doing it? You see, this epsilon, it takes the responsibility of uh, of uh, of capturing uh, the small deviation from this y. So we could have written like this: y plus eta. Okay, so this eta is the variation on this y, but we want to really ensure that this variation is only a little bit of a variation. So this y, ultimately we are going to set it to be a very small value, and that will actually uh, uh, be a mathematical representation of the fact that we are trying to explore the near neighborhood of this y. Okay, so let me proceed with it. The whole idea will become clear as we proceed to the steps. Okay, so if for y we have this I, then for this y plus epsilon eta, we have this I bar, where this I bar is dependent on x and on this neighboring curve y plus epsilon eta. Very importantly, you note here that this eta itself is also a function of x. Okay? But the epsilon is not a function of x. Okay, so it's something like this, that you are taking a curve like this is our y, and then you are taking maybe a curve which is like this, or maybe something like this. Okay, these are the neighboring curves. All right, so I have drawn it in a very arbitrary fashion here. This is my x and this is my y, and like specifically this is my y, and these are my the other things, the other curves are the neighboring curves. Okay, now just like as we had mentioned in the case of extremization of functions, what we want to ensure is that for minimization, and the process will be exactly the same for maximization and in general for extremization. So for minimization, sorry about that. For minimization, we need to ensure that I bar minus I must be greater than 0. Because if our answer is indeed the specific y, then this I must be taking the smallest value. So no matter what other I bar value there is, it should always be larger than that y, than that I. Okay, so exactly proceeding with those ideas which we had discussed in our previous lecture. Okay, now uh, what are the uh, what are the inside details uh, which which we need to take care of uh, for this kind of a thing. Okay, so what we'll say is that this I bar, okay, so writing it properly, so our integrand is f x y dash, uh, and our I bar is okay. So now we'll do simply what we need. Okay, absolutely utilitarian approach, nothing fancy mathematically. We'll just do a minus of these two things. We'll do a minus of these two things, and then we are going to do a Taylor expansion. So step by step. Okay, so we are going to do a Taylor expansion on this. So the first term here is fx y dash plus then we have the first order terms, epsilon eta by factorial 1, del f del y uh, plus epsilon eta dash by factorial 1 del f del y dash. Very importantly, please note that here the dependence of f is on y plus epsilon eta, and y dash plus epsilon eta dash separately. Similarly, here the dependence of f is on y and y dash separately. So generally, most of us, when we first start learning this, we have a wrong notion that because f is dependent on y, the dependence on y dash is automatically ensured. That is not so. And because that is not so, because the dependence on y and y dash need to be explicitly and separately mentioned, it is as if y and y dash act like two separate variables, which is why in the Taylor expansion also we have to treat them separately like this. Okay, for the next uh, the second order terms, the what we have is epsilon square eta square by factorial 2 del square f del y square plus epsilon square eta dash square by factorial 2 del square f del y dash square, and then we have two terms involving the cross derivatives. What I mean to say is that we have one term which is like del square f del y dash, and another term which is which involves del square f del y dash del y. And because the order of the derivatives do not matter, what we end up is with this is 2 epsilon square eta dash. So it is like epsilon eta times epsilon eta dash from the two separate terms by factorial 2 del square f del y dash. Okay. And then for the higher order terms, we represent them through this order notation where we understand that this all these terms are of order epsilon cube. So we close this bracket here, this is dx, and then we have this last term, integration x1 to x2 f x y dash dx. Please note very quickly that this first term here, it cancels with this last term, so that what we have here can be represented in a slightly more convenient notation by taking this this epsilon term common. So what we end up with here is epsilon eta del f del y plus eta dash del f del y dash plus the epsilon square terms, and you please note that in each of these epsilon square terms we have a half factor common, so we take that out also, and what we have inside is eta square del square f del y square plus eta dash square del square f del y dash square, and then of course we have this term, this twice eta dash del square f del y dash. So and what we are going to do here is we're going to take this order epsilon cube term outside, not worrying too much about the integration. Okay, so as a last step here, we can write this as so I can write this as epsilon eta del y plus eta dash del y dash, whole thing operating on f, and similarly here half epsilon square. This one I will write like so I'll write this as a perfect square, again in the form of an operator, So just the square of this. So I missed the dx here. Okay, so usually what is done is to uh, write this particular thing, which you remember that this is nothing but I bar minus I. Uh, this is usually written with the notation that this first term is like the first variation of I. Okay, so this is the usual notation delta I. So that captures this integration x1 to x2, this entire term with respect to dx, and this second term here, that is written like the second variation on I. Plus of course we have this ordered epsilon cube term. Now we are at the same juncture as we were in the uh, extremization of functions, uh, as we had discussed in the previous video. Uh, so again, what we are going to say is that epsilon is tending to 0. So epsilon is very small, which means that this term delta I, which is actually dependent on this epsilon, the first power of epsilon, that is going to dominate over this term, which actually contains within it the dependence on epsilon square. Okay, because epsilon is very small, it is tending to 0. So for example, if epsilon is like something like 0.1, you can understand that square of that is even smaller, 0.01. Now if this dominates over this, okay, and uh, uh, going back to our previous argument where we said that this uh, first order term, that would be having a variable sign, so also here this delta I term, uh, it could have a variable sign depending on the sign of epsilon. Sorry about that, my slide just jumped ahead. uh, so as I was saying that this delta I, since it depends on epsilon, uh, its sign will be determined by the sign of epsilon. But we don't want that, because if that were true, then sometimes this term would be positive and sometimes it would be negative. But we want to ensure that I bar minus I for our minimization problem must always be positive. So since our delta I is dependent on epsilon and its sign is also given by epsilon, so we have to ensure that its influence on I bar minus I is switched off. And the way that we can do it is, so we require that delta I must be equal to 0. So there is a little bit of a difference in the way that we have written this condition. The delta I is equal to 0. Earlier we had only isolated the derivative term in the extremization of functions, but here in extremization of functions we are saying that the whole term must be equal to 0. But ultimately we'll see that it'll just give us something equivalent to extremization of functions. And further on, again exporting the same kind of idea from the extremization of functions, if we want to really ensure that I bar minus I is indeed greater than 0, then all that we have to ensure after ensuring that delta I is equal to 0 is to say that delta square I must be greater than 0. Now that is something which we won't require uh, in most of our discussions of advanced mechanics of solids, so we'll relegate it for some future discussions. For now, we are going to concentrate on this requirement, that delta I, the first variation of I, so to speak, so that's how it is conventionally referred to, the first variation of I, that is equal to 0. We want to focus on it. So delta I is equal to 0. So delta I equal to 0 basically means that we are dealing with this term epsilon eta. You just take a look here, epsilon eta del f del y plus epsilon eta dash del f del y dash dx x1 to x2, that is equal to 0. Now we'll do a little trick here, and this is a trick which we'll do time and again over an entire study of advanced mechanics of solids, and really whenever we have to use calculus of variations even beyond mechanics. So we are going to do an integration by parts. We're going to do an integration by parts over this. Okay, so just wait and watch what happens. So we'll take this epsilon del f del y dash as our first part, and so the integration will be carried out over the second part of eta dash, and that will give us eta. So this first part, that doesn't change, keep it like this. So this is epsilon eta del f del y dash and then we have minus. So now we are going to do a derivative over this epsilon del f del y dash part, so ddx of epsilon del f del y dash, and of course the integration over the eta dash has been carried out to obtain a eta, and again integration over this. The benefit of carrying out this integration by parts now is that we in all the terms involving the integrations, we now have the presence of this eta here, instead of the different things, the eta and the eta dash, which was earlier present. Now please remember that we are focusing on the condition that the first variation of I is equal to 0. Within this condition, there could be two cases depending on how we deal with these boundary terms. So the first case, the first possibility, case 1, is when our y is such the nature of y is such. So what I'm basically saying is that the admissible curves are such that the values are actually specified at the boundaries x1 and x2. Okay, so values of the curve are specified at the boundaries. What does that entail? That means that when we are taking a another choice of our curve like this, the eta should be such that when x is equal to x1, eta is equal to 0, and when x is equal to x2, eta is also equal to 0. That is what is basically meant by this statement, that the values of the curve are specified at the boundaries. So it is as part of our characterization of the curves that we are dealing with, that will be given. Okay, and this will have direct consequence in our development of our beam theories and our plate theories, as far as the boundary conditions are concerned. You will see when we go into that. So this is a very important and subtle part which you must appreciate. Okay, so written currently in this abstract mathematical fashion, it may not seem, I mean, what is going on here, I mean, we are just choosing something arbitrarily, but it is not like that. Okay, so when we actually connect it to our theories of beams and plates, it will become much more evident and clear. Okay, so here the y plus epsilon eta should be such that eta is equal to 0 at x1 and x2. Now the moment we write this thing, that eta is equal to 0 at x1 and x2, you note what happens to these boundary terms. So this is basically eta, epsilon eta del f del y dash evaluated at x2 minus epsilon eta del f del y dash evaluated at x1. So both of those terms, they go to 0. So therefore epsilon eta del f del y dash x1 x2 is basically equal to 0 minus 0 equal to 0. So all that we end up with uh, is just this first term and the second term, and please note that I have forgotten to write this equal to 0 here. That should be present. So what we have effectively is epsilon eta del f del y minus ddx of epsilon del f del y dash eta dx integration x1 x2 equal to 0. Okay, now of course epsilon is a constant, so it doesn't really matter, we can take it out of the integration, but it's very important to note what happens to this eta, because that is not a constant. It is not a constant, but very usefully, eta is arbitrary. And because this statement, this integration must be true for any arbitrary choice of eta, therefore it follows that this integrand must be equal to 0. Okay, so it is very much possible to go into a far more formal kind of logic behind showing this, but again, I'm going to take up an utilitarian approach, and just uh, say here that since eta is arbitrary, uh, so the only way that the zero value of the integration is possible, zero value of the integration is possible is if del f del y minus d dx del f del y dash that is equal to 0. So the integrand itself uh, without the eta, that itself is equal to 0. And this condition, okay, so this condition del f del y minus d dx of del f del y dash, this is equal to 0. This is the famous Euler-Lagrange condition, or the Euler-Lagrange equation, which will use time and again all through our applications of calculus of variations in advanced mechanics of solids. Okay, so this is just the case 1. What about the case 2? The case 2 is where uh, y is not specified. At the boundaries. So we certainly do not require that eta has to be 0 at x equal to x1 and x equal to x2. So if we go back and take a look at the condition which we had obtained here, so we can club these two together, but we really can't set this to equal to 0. Okay, like I mean uh, based on any conditions on eta, but it still remains true that this integration plus this boundary term must still be equal to 0. So how do we go about doing it? So all that we have to do is to take up this integration together, set that equal to 0, and take this boundary term and set that equal to 0, and overall that will ensure that the whole thing is equal to 0. Okay, so let me just try to copy this thing here. Okay, so what I'll do is I'll club these integration terms. So epsilon eta del f del y minus d dx, exactly like before, where of course I have taken out this epsilon from this first bracket here. In order to ensure that this result is indeed equal to 0 for arbitrary choices of eta, uh, what we have to say is that uh, this will be 0 if, so again understand that eta is very much arbitrary here. Okay, this will be 0 if del f del y minus d dx del f del y dash that is equal to 0. So individually this part of the integrand here is equal to 0. That will ensure that this integration is 0. And considering this boundary term, again since this eta is 0, we can't do anything with it, but we can ensure that this is equal to 0 by ensuring that del f del y dash is equal to 0. And again you will see that this rather mathematically abstract way of thinking about these equations will have a direct consequence in terms of the physically very much tangible things that we talk about when we deal with beams and plates. Okay, and particularly with reference to how the boundary conditions emerge. All right, so as far as the as the basic development of what we require in the calculus of variations, that is done here. Okay, so uh, the bottom line here is that we have arrived at the all important Euler-Lagrange equation. You please note that this again here is the Euler-Lagrange equation. And depending on what kind of a case we are dealing with, uh, we uh, we will be happy just by dealing with the Euler-Lagrange equation, or we'll have to deal with this case where we have an extra condition at the boundaries that del f del y dash is equal to 0 at, let's not forget this, at x equal to x1 and x equal to x2. Okay, now I mean, had we been doing a more mathematical course uh, involving the calculus of variations, then certainly we would go about applying these kinds of equations directly to some problems, some very classical problems, including the Brachistochrone problem. But right now, I will not invest any time on that, as you will see that we will be constantly running short of time. We'll be chasing to will be kind of a constant chase to finish our syllabus here. So unnecessarily, I will not invest any time on applying this thing on very general mathematical problems. Rather, as quickly as possible, I'll try to apply these things to directly what we need in advanced mechanics of solids. On that note, let me finish up this lecture. Thank you very much.